this video, I want to go through an overall summary of engineering dynamics. And what I really want to do is just kind of hit the highlights of more or less everything that's been covered through this video series. So within the very broad field of engineering dynamics, there's kind of two main divisions that we want to think about and need to consider when we try to solve dynamic problems. And those are kinematics and kinetics. So kinematics is, or could be defined as, the geometry of motion. So when we say geometry of motion, basically, the ways that things move, the way that maybe a particle, for example, moves around a curve and how that influences maybe the linear portion and the curvilinear portion of that motion and how those things relate to each other. Kinetics, on the other hand, refers to the causes of motion. So for there to be motion, there has to be something producing that motion. And that's where we start to talk about kinetics and how forces or torques or other inputs lead to motion of a particle or a rigid body. All right, so thinking back to basically everything that's been covered in dynamics, one of the areas is linear translation. So this is kind of the first simplest step for starting to think about how things might move. And linear translation is really talking about straight line motion. It also has some simplifications that we might want to think about, such as constant velocity, as well as constant acceleration. And recall that constant velocity gave us an equation for position, which looks something like this, and constant acceleration gave us a similar looking equation for velocity, a new equation for position, and also a variation on these equations which removes time specifically from that system. So these two assumptions, constant velocity and constant acceleration, are often useful for many different types of problems that we might try to solve, and they're useful approximations for a lot of different scenarios. So if we have some sort of driving force, for example, that might be giving us some constant acceleration, so kind of we might jump back and forth between the force and the acceleration and what that means, and then analyze the motion using constant acceleration. Constant velocity, assuming there's no external things acting on this on the object, then we may have a constant velocity scenario. After linear translation, we talked about curvilinear translation. And curvilinear translation, the primary consideration that we added to our understanding is normal and tangential accelerations. And for a simple particle passing around a curve, we talked about how the normal acceleration was related to the change in direction, while the tangential acceleration is most closely related to the change in speed. And so we developed an understanding of how those two things work together to form a net acceleration for our object. And as this object both possibly changes speed and changes direction, both of those things get factored into that acceleration consideration. We also talked about projectile motion. And projectile motion, you can think of it kind of as a curvilinear translation, in that, under a standard model, our projectile would travel on a curvilinear path. The projectile motion could be approximated in many cases by saying that the x direction has no external forces or things applied to it, assuming that we neglect air resistance or drag, and therefore we assume constant velocity, which we talked about just a second ago. And in the y direction, which would be our vertical direction, we assume perhaps that there is only the acceleration of gravity, or the force of gravity, acting on our object. And if we have a force, then we know that that leads to an acceleration. So therefore, we may assume constant acceleration. Now, of course, for some systems, some type of problems, we may not be able to make these assumptions, right? Air resistance may not be negligible, or maybe we have a propelled object, so like a rocket or something like that. Maybe we have changing mass because of the rocket consumption of fuel and things like that. So those situations maybe aren't suitable for these approximations, but we have to decide when we can make these sort of simplifying assumptions. Another form of relationship that we've looked at includes both dependent and relative motion. So dependent motion, as an example, if we have an object attached to a pulley, and for example, if this mass on the left is moving up, then because of the pulley, we know that the mass on the right is moving down. We may also know other things about the system. If we assume that the pulley is massless, or rather low mass relative to the suspended masses, then we could say that the tension is maintained in the rope, and that gives us a little bit more information. We also saw relative motion, where, for example, we might have one object moving with some velocity, and maybe we have another object moving with some different velocity, and we want to understand the relationship between those two. And we saw that we could say that the relative velocity, let's say of object 2 with respect to object 1, is written as the velocity of 2 minus the velocity of 1. It's also important to remember that these are vector quantities, and therefore, if they're not headed in the same direction, so the picture different from the picture I drew here, say I have v1 headed this way and v2 headed this way, those vector quantities allow me to represent this system using a vector diagram. So, for example, I might say that v2 is equal to v2/1 plus v1, so a rearrangement of that equation. And therefore I might say, okay, if I have v2 that looks like this, and I'm going to add or take v1, and then if I add v2/1 to this, I might get a vector diagram that looks like this and allows me to solve for my unknowns. Any any vector diagram like this in two-dimensional space allows me to solve for up to two unknowns because I have two orthogonal direction equations, for example, x and y components that I could write equations for. So that's two equations, and it lets me solve for two unknowns. All right, so a lot of these things that I've talked about so far, we're specifically looking at projectile motion or particles or relatively simple objects for which rotation isn't really a consideration. And therefore, we also had to factor in what happens when we take rotation into account. The first version of that was looking at fixed axis rotation. And in its simplest form, we might say there's a disk or a wheel that rotates with some angular velocity omega. And the main difference that occurs with fixed axis rotation is that we have position theta, velocity omega, and acceleration alpha instead of their linear components, which might be position x, velocity v, and acceleration a. Now we saw when going through fixed axis rotation that we can apply many of the same equations. We can apply relative motion, we can apply constant velocity, constant acceleration type conditions, and basically just swap out the variables, and it works in the exact same way. We also know that, for example, if I have a point on this circle and I want to know how it's moving at that very instant with its velocity v, I know that I have a relationship between the two, linear components and the rotational components in this case, as x relates to theta by the radius, so does velocity and acceleration in the tangential direction at least, looking like that. We do, though, have to add in the change of direction for the acceleration, and we saw that the equation for that looks like this, r omega squared, which could also be written as v squared over r. All right, so we've added in the rotation component. So what happens when we put that all together? Well, we get something that we call general planar motion. And general planar motion most simply is translation plus rotation, all happening at the same time. And what we saw with our initial analysis of general planar motion is that we can break those two things up. We can consider the translation of, say, a rigid body and the rotation of the rigid body separately. And when we do that, we can then relate them back to each other using that concept we just talked about of relative motion. And from relative motion, we can solve for the net result of how this rigid body or a rigid body is moving. We also saw the concept of instantaneous centers of rotation. And recall that the instantaneous centers of rotation basically means that we define a point or find a point that at any instant in time a rigid body undergoing both translation and rotation can be said to be rotating about without translation. Now, of course, as the body translates, this instantaneous center must move as well. But for any instant in time that we're looking at, we can approximate, or not even approximate, we can say that that motion is a fixed axis rotation. And that allows us to do some calculations using the principles that we just talked about. We also looked at energy methods. And energy methods for solving dynamic problems involve finding potential energy, kinetic energy, and work. done from a system. So potential energy could be change in height, which is mgh, for example, or it could be stored energy, such as in a spring. Kinetic energy is motion. So velocity of an object gives us an understanding of the kinetic energy. And then this U1 to 2 term represents work, or change in the state of an object. So if something is moving with some kinetic energy and we apply work to it, we get some sort of change in that state, maybe a different velocity, for example. Gravity is a common source of work. Now, of course, realizing that gravity shows up in potential energy as well, and we don't want to consider it in both places at the same time, but it's a different way to think about it. Work also can come from an applied external load. Remembering that work could be, for example, force applied over a distance, or maybe torque applied over some change in angle. Within energy, we saw that we could use the conservation of energy, which came in the form of potential energy plus kinetic energy in state 1 must be equal to potential energy plus kinetic energy in state 2. Or, thinking about this another way, we could say kinetic energy plus some work added to or subtracted from the system equals a new kinetic energy. And both versions would give us the same outcome. It's just a different way of thinking about what sort of things we might add to or subtract from our net energy. We also looked at impulse and momentum as another way to think about dynamic problems. So, impulse is a force applied over some period of time, and momentum, most simply, is a mass times a velocity. And we saw that conservation of momentum, much like conservation of energy, applies here as well. So the momentum before plus some impulse must equal the momentum after. Recalling that this equation could be written as a summation if there's more than one object involved. So for example, two balls colliding and then separating, we could consider that system as well and say that each ball has momentum before and after the collision. We also saw that we could say, in that impact, there's maybe a coefficient of restitution, for example, that tells us the efficiency of that impact, how much energy is retained versus lost into noise, vibration, heat, things like that. And so far we've talked about kind of three big major ways to solve problems, right? And therefore, we sometimes want to think about, well, which method is appropriate to use, right? We have considerations for whether or not we know things about acceleration. Do we know how much time was involved in whatever is happening? Do we know something about distance? And each of these things might give us ways to solve a problem via, for example, Newton's second law, impulse and momentum, or work and energy. So whether we're talking about, for example, forces leading to accelerations, or a force applied over a short period of time causing some change in velocity, or a force applied over a distance causing a change in velocity. These different methods of thinking about a dynamic problem all work together, but they're differently applicable under different situations. So depending on what we know about a system at any given time kind of helps us choose which of these methods might be most appropriate to solve a problem. All right. Next, we jumped into a discussion of vibrations. Vibrations being a major topic of engineering and a major consideration that we have to think about. We saw that vibrations can be undamped or damped, basically whether or not there is the presence of a damper. And we recently saw that a material itself could be both a spring and a damper for viscoelastic materials. We had basic form equations. For example, in the undamped scenario and in the damped scenario. And the only real difference here is that we've added in this damping term, damping coefficient, which is a function or acts on the velocity of the motion, x dot. Now, thinking about the frequency of vibration is useful in that we may need to know the natural frequency, and we saw that the main reason for that is that at the natural frequency we may see resonance, where if we have a forced input, we would get some sort of unstable large oscillation. If it's not a forced input, then the natural frequency is basically how we expect the object to move once it's been perturbed from its equilibrium position. For undamped motion, we would expect to see some sort of sinusoidal output, and we also then talked about how undamped vibration doesn't really happen in reality, because basically every system has some sort of damping, because even a really elastic spring is going to have energy loss due to the deformation of the spring, due to sound, things like that. So in reality, we would expect to see damped motion. And for example, an underdamped system might have an output that looks like this, where the oscillating position is contained within an envelope that represents the damping of that signal. We talked very briefly about material response to dynamic loads, and specifically looked at viscoelastic materials, where we have some unique properties. And we saw that a couple of considerations that are interesting to look at: stress relaxation and creep, as different ways that viscoelastic materials may respond to dynamic input. And we also saw that this principle of creep can give us an understanding of viscoelastic phase lag. So if a viscoelastic material represents basically a spring and a damper together, then we would expect it to behave like a damped system. So seeing that output and those results is kind of useful for furthering our understanding of engineering principles and engineering systems. So the overarching theme, I think, that we want to think about when it comes to dynamics and solving dynamic problems is that it mirrors very much engineering problems as a whole. We have to consider what we have going on in our system. We have to consider what sort of assumptions, perhaps simplifying assumptions, that we may be able to make in order to allow us or make the problem solvable. Sometimes we need simplifying assumptions just to make it solvable. And then we need to consider what sort of applications we have. Are we looking at a system with cyclic motion that we want to model as a vibration? Is Newton's second law most applicable, or would this problem be easier to solve using conservation of energy? Is it a rigid body such that rotation is important, or is it a particle where we don't really worry about rotation? Is it projectile motion? And is there any sort of assumptions like constant velocity or constant acceleration that we can make? Once we've defined our assumptions, then we can start listing out equations and looking for what are the known quantities and what are the unknown quantities. Obviously, to be able to solve a given problem, we need to have an equal number of equations and unknowns to make it something that we can work with. So sometimes we may find ourselves with too many unknowns, and we can use things like dependent or relative motion to add something, add a relationship between two of our variables that eliminates that extra unknown. But the net result is that it looks like a lot of engineering problems, in that we need to list our assumptions, figure out what we know and what we don't know, and figure out what appropriate theory is applicable. And of course, in the end, it doesn't always mimic real life all that well. There's often too many unknowns in a real life problem, and these assumptions are really the only way that we can make sense of it and arrive at something where we can try to predict what's going to happen. So hopefully this review has been useful for you in thinking about kind of the broad picture of dynamics. Hopefully the video series has been useful in helping in small ways our understanding of dynamic systems and how we analyze motion. Thanks.